Let's talk about speed. So, when it comes to speed, it's time to discuss two different kinds of speed, two different kinds of velocities, especially when objects are traveling in a circular path. So, like if you think about that goat problem I did earlier, where you have a goat tied to, so here we go, this is my goat, tied to a stake, and the goat goes around in a circle over and over again. Whoa, that is not a circle, but you know what I mean. So there is two kinds of speed. One is considered linear speed, and that would be how far did the goat travel if he was traveling in a line. So this over that's the linear speed. Is how far did someone travel if they were traveling in a line, which means basically how fast are they traveling if they're traveling in a line. So the definition of linear speed is how fast an object is moving if it was moving in a straight line. So you basically are looking for a distance divided by time. Now, angular speed is something very different. It is now looking at this, at the angle. It doesn't care about how far the goat is away. In fact, if there was a little tiny mini goat right here and they were walking side by side next to each other, so here's a baby goat, if they were basically walking side by side, this mini goat would have a much lower linear speed because it's on the inside circle, but it would have the same exact angular speed because it's always moving at the same exact rotation. It does the same rotations. So this over here would be your, the definition would be your basically rotations. Over a period of time, and the formula is basically your angle measurements right there, angle measurements over time. So now let's talk about how this would look like in some of our problems. So let's look at this Big Ben problem, and you guys should be all familiar somewhat with Big Ben, which is basically the clock tower. But we're going to talk about specifically the clock in there, and read through it really quick. Pause me. But when we're looking at the linear distance of the tip of that minute hand, we basically first have to figure out how far does it travel. So first, I'm going to go with 2 pi r, right? And our r is basically your 14 feet, right? We got that from here, 14 feet. So times 14 feet. That is how far we travel. So maybe I should add that. So 14 feet. This is 1 circumference. How far we travel. Now, this is per, so I'm going to say divided by 1 hour, right? Because every hour we travel this far. But now I want to know this during a 12-hour day, so I'm going to multiply this by 12 hours in 1 day, or in a 12-hour day, so to say. So that will give us 336 pi feet per 12-hour day, right? Which is going to be, roughly speaking, this distance right here, 575 feet per 12-hour day. Okay, not 24-hour day, that would be double that. Okay. Now, what is the average speed? Well, the average speed, first of all, what units do you want? So I'm going to figure out a distance, which is, again, 2 pi times 14 feet. So my 2 pi r divided by, let's go with 60 minutes, because this is per 1 circumference, right? Or rather, let's set it up properly. This is by y circumference but I'm doing one circumference, right? Or one all the way rotation, one rotation, so to say, per 60 minutes. So therefore, our speed is going to be 28 pi feet per minute. Divided by 60 minutes, which is going to be, roughly speaking, 28 times pi divided by... All right, which is roughly going to be 1.466 feet per minute. By the way, if you wanted to do it by hour, right, so this is a correct answer. If you want by hour, we would multiply it by 60 minutes per 1 hour, and we would get, therefore, 87.965 feet per hour. All right, now what is the angular speed? So that is where we take 360 degrees and we divide it by 60 minutes and we get 6 degrees per minute. So degrees per minute. Now, compare the linear and angular speed of the tip of the minute hand of Big Ben and a regular watch. Now, a regular watch we're talking about is very, very small, right? I mean, like we're talking inches. Now, here's a neat little thing. We must have the same angular speed. If it is not the same angular speed, we're not talking about a good watch here. It must be the same angular speed. All right, but Big Ben would have a much, much bigger, and I'm talking significantly bigger linear speed than small watch when it comes to linear speed. So that is pretty much big. That is pretty much it. And here, in for unit comparison, object A has a higher angular speed, while object B has a higher linear speed. Name some examples of A and B pairs in the world. So object A could be a skateboard. So A, skateboard, and B, let's say, is a bike. Now, when you think about it, a skateboard going just a little bit slower than a bike, like slower meaning linear speed, the wheels will be turning much, much quicker. So the skateboard wheels would have a higher angular speed than the bike's wheels, but the bike would be traveling much faster. That would be one of the examples there. Alrighty. So, good luck. Try these out for yourself. These are some really, really neat problems here. It takes a little while to get your head wrapped around this, on how to convert it, but I mean, in engineering world, this is how things work. In your engine, there is several things spinning, and that's what makes the car basically go, is this conversion of angular speed into linear speed. For those of you who had gear bikes, right, like this might seem familiar to you from a gear bike, this is how your gears work. You're adjusting angular speed into linear speed depending on how big the cog really is, and so on. So